Good afternoon, and welcome to the third and final day of the 2020 Schawlow-Townes Symposium. There will be two components today. First will be two talks, and they will be followed by a poster session given by our PhD and postdoctoral students. You will want to attend both, and you will have to leave this meeting and click on another meeting to try the poster session, where you'll be given a room for each of the posters and you can enter any room you wish. The only thing you must remember is to upgrade to Zoom 5.3 in order to be able to go from room to room to room to room. There will be a question period after each talk, but of course the first talk is Professor Tsai from Asia, and he will not be here in person. So let me ask you to write your questions in the question and answer period as they occur to you, in the middle of the talk if you wish. And we will leave a few minutes also after the talk for you to add questions to it. And we will send the questions and get his answers and send them directly back to you. So although we can't have a in-person or a live question and answer, we can do sort of the next best thing to the question and answer. I mentioned about the poster session. And you have a special link for the poster session. So our first speaker is Professor Tsai. Professor Ding-Ping Tsai is the chair and head of the Department of Electrical and Information Engineering at Hong Kong Polytechnic University. He is elected a member of the International Academy of Engineering and the Academy of the Asia Pacific Materials Science. He's an author of 316 papers, a number of books, chapters, and technical reports. But what really impresses me is he is also an author of 67 patents, 20 of which have been commercialized. Isn't that amazing? 20 patents commercialized. He received prestigious recognitions, including the 2019 highly cited researcher by the Web of Science. He was China's top 10 optical breakthroughs of 2018. He won the Mozzie Award from the International Society of Optics and Engineering. Maybe we mostly know of it as SPI from the SPIE. And he has the Future Tech Breakthrough Award from the Ministry of Science and Technology in Taiwan in 2017 and 18. He currently serves as an editor of the Progress of Quantum Electronics and a number of other journals as well. His talk will be a virtual talk, as you can imagine, because he cannot be, or at least you can't expect him to be awake in the middle of the night. So we'll now go to his talk, and that will be put on, I think, by Dr. Sederberg.
Good afternoon. Many thanks to Professor Paul Corcoran, Professor Robert Boyd, and Professor Pierre Berini for the kind invitation of my talk at Schawlow-Townes Symposium in the University of Ottawa, Canada today. I am Ding-Ping Tsai from the Department of Electronic and Information Engineering, the Hong Kong Polytechnic University, Hong Kong. I was very much looking forward to attending this important event. It is my great honor and pleasure to present my talk, Meta-Lens, An Eye to the Future. I will report the current progress of our research group on the development of optic meta devices, especially the Meta-Lens, and their application in light field sensing, imaging, and quantum optics. First, I would like to thank my graduate students for their great efforts on the results shown and the report in this talk, and also our research collaborators around the world, including Nanjing University, Hokkaido University, Rice University, Caltech, Nanyang Technological University, University of Southampton, National University of Singapore, University of Massachusetts Boston, Fudan University, Harbin Institute of Technology in Shenzhen, Academic Sinica, and National Taiwan University. This is the outline of my talk. I will first give a brief introduction of meta-surface and the generalized Snell's law and their applications of meta-surface. I will show you the reasons for developing the meta-lens and achromatic meta-lens. I will provide you the general design principle of meta-lens. After that, I will report how to use differential phase equation and edge alignment method to make our achromatic meta-lens for reflection. Similarly, I will show you how to make our transmission type achromatic meta-lens and the meta-lens array for light field sensing, imaging, and the quantum optics. Finally, I will summarize my talk with the prospects of meta-lens. I will first give a brief introduction of meta-surface and the generalized Snell's law. In the textbook, the Huygens-Ferney principle says that every point to which a luminous disturbance reaches at the interface will become a source of a spheric wave, and the sum of these secondary waves determines the form of the wave at any subsequent time. The Snell's law is based on this simple principle for a perfectly flat interface. That is, for the normal incident case, the generated wave will be in the same propagation direction as the incident wave. However, for the interface with metastructure, extra k-vector is generated, and the sum of the propagation k-vectors determines the propagation of the incident wave. This is so-called generalized Snell's law. In 2011, Dr. Nanfang Yu's science paper showed that meta-surface with narrow antennas was used to demonstrate the wavefront of the propagating wave can be fully controlled. 8 different narrow antennas can generate 8 different phases to form a new wavefront. It means that arbitrary wavefront can be generated by the design of artificial narrow antenna at the interface. Of course, the size and the period of the narrow antenna are small compared to the working wavelengths here. In general, meta-surface with narrow antenna can be used to generate different phase polarization, amplitude, optical, angular momentum, and so on. That means the incident electromagnetic wave can be manipulated by the specific designed meta-surface for various optical applications, such as imaging, wavefront correction, structure color, sensing, optic communication, and display, so on. Applications of meta-surface. For the applications of meta-surface, we have demonstrated the gradient narrow antenna metasurface for the beam deflection, and the full-color meta-hologram. We show the versatile polarization generation and analysis, generation of the toroidal dipole and anapole, and the pixel-level full-color routing using various novel meta-surfaces. We also demonstrate the epsilon near zero tunable metasurface for beam diffraction. In this talk, I mainly focus on the design, fabrication, and application of the broadband achromatic metalens and metalens array. Metalens and achromatic metalens. Why metalens? In our daily life, optic lens can be seen everywhere. For example, camera, mobile phone, microscope, and so on. For full-color imaging, a wide-band working wavelength is needed, and the chromatic aberration appeared due to the dispersion of the material. To solve this problem, people normally have to design a complicated lens set to have aberration-free full-color wideband image. This also leads to very complex design and bulky system. However, metalens use the narrow antenna of metasurface to manipulate the light. It is flat optics without spheric aberration. The narrow antenna acts as the secondary light source for the light emission, which can be polarization dependent. The polarization image can be easily achieved. The advantages are lightweight, compact size, novel function, flat optics, and the CMOS mass production process compatible. In 2015, different narrow antennas were used for the focusing of the various wavelengths. They show the combination of different narrow antennas had the same focusing position for a few discrete wavelengths. Subsequently, for the achromatic focusing purpose, 3 metasurfaces were used for the focusing at the same position. The problem here is the focusing efficiency after going through 3 metasurfaces is quite low. In 2017, the combination of various nanostructures can achieve an achromatic metalens with 60 nanometer bandwidth in transmission mode is shown. However, in principle, to realize achromatic meta devices in a wide range of frequency is possible. General design principle of meta lens. If we consider the meta-surface devices as a transformation tensor matrix, the output can be calculated with the known input. The solution of wavefront transformation can be found. In this case, we have the demanding output of the focused optic field and the known input. The solution of the transformation tensor matrix of metalens can be found mathematically in principle. However, in reality, how to realize the solution of the transmission tensor matrix of this metalens can be very challenging. The proposed meta device may have multi-modulation requirements, such as amplitude, phase, polarization, orbital angular momentum, high harmonic nonlinearity, or even quantum entanglement effect, and so on. In case you try to combine various nanostructures to be the integrated resonance unit to satisfy all the demanding specifications. Optimization is needed at certain point in order to accomplish practical and useful meta devices with high efficiency and novel functions, such as achromatic or chromatic, polarization conversion, vortex beam generation, quantum entanglement, nonlinear signal generation, and so on. I share with you our design principle here. No matter what kind of materials used for the nanostructures, with the known epsilon and mu, one can find the wavelength-dependent refractive index and extinction coefficient N and K. By using the simulation software such as CST and console multiphysics, the transmission and the reflection spectrum can be found for the nanostructures with known geometry and configuration. All the data collected can form a big database for the information on efficiency, phase, polarization, and the integrated resonance unit, IRU. Subsequently, with the known specifications of meta devices, limitations of fabrications, that is, critical dimensions and the empirical parameters of production process, we calculate and design the layout of the narrow antennas for the meta devices. This layout file can be readily used for either e-beam lithography or photo mask of CMOS compatible production process. Mass production can be done with high precision. Finally, the meta device we design, calculate, and fabricate have to be characterized and measured before the applications. Achromatic meta lens for reflection and the differential phase equation and the edge alignment method. After sharing our design principle of meta device, I would like to share the first case of our continuous broadband achromatic meta lens in reflection mode by using the differential phase equation and edge alignment method. In this case, we achieve focusing with no chromatic aberration over a continuous broadband wavelength from 1200 nanometer to 1680 nanometer. As you can see here, to implement the achromatic meta lens focusing, we use multiple antennas to form an integrated resonance unit instead of single narrow antenna, and also the PB phase effect to successfully accomplish the continuous broadband wavelength focusing. Follow the design principle I share with you. An achromatic meta lens with diameter of 55 micron is shown here with optic image and SEM picture of the narrow antennas. There are more than 60,000 narrow antenna units in this meta lens. The unit antenna consists of a gold mirror underneath, a 60 nanometer silicon dioxide dielectric layer, and 30 nanometer thickness gold antenna sets on the top. There are 23 different features of the narrow antenna unit used in this broadband achromatic metal lens. For example, the Type A narrow antenna units consist of the 10 narrow antennas with 40 nanometer width, 450 nanometer length, and 25 nanometer gap distance, which is used for 30-degree phase compensation purpose. From the center to the edge of the lens, there are 50 different zones with the chosen narrow antenna unit type and the specific rotation angle for PB phase. The design principle of our achromatic metal lens is shown here. We use the traditional focusing equation for the optic phase as the function of the metal lens radius r and wavelength lambda. We use the differential phase equation, and this phase function can be shown in two terms. One is for the basic phase control. The other is for the phase compensation purpose. We intentionally align the edges of the phase function curves of the maxima and the minima wavelengths to have the large phase difference happen in the center of the meta lens. To realize an achromatic meta lens working in a wide and continuous wavelength, as mentioned in last slide, two terms of the differential phase equation. One is related to the lambda maxima, which is independent to working wavelengths. We can use PB phase method to control and fit the phase curve. That is by rotating the narrow antenna theta angle to have 2 theta phase change. The second term is closely dependent on the working wavelength, which can be considered as the phase compensation between different wavelengths. It is the most challenging part. We have to provide the required phase compensation with an integrated resonance unit, IRU, to satisfy this condition. With the use of the differential phase equation, edge alignment method, Berry phase control, and integrated resonance unit, the lookup table of all the building blocks and the parameters can be calculated and generated as this one I previously showed to you. This is the achromatic metal lens made by our design. The optical and SEM images are shown here. From the SEM picture, you can see the different integrated resonance units at different positions for special phase requirement. The diffraction limited focusing spot of the wavelength of 1.5 micron is shown. The achromatic focusing can be observed from experimental and theoretical results, and which agrees to each other very well. We also measure the other two achromatic metal lens with different numeric aperture values. Excellent achromatic properties can be observed. For comparison, we show The chromatic meta-lens results based on only pure Berry phase design. They show the different focal lengths for various wavelengths and a very clear chromatic aberration. Following the similar design principle I shared with you, the second achromatic meta-lens with diameter of 41.86 micron is shown here, with optic image and SEM picture of the narrow antennas. The working wavelength is from 400 nanometer to 670 nanometer. There are more than 34,000 narrow antenna units in this meta-lens. The unit antenna consists of an aluminum mirror underneath, 40 nanometer silicon dioxide dielectric layer, and 40 nanometer thickness aluminum antenna sets on the top. This is the lookup table of all the building blocks and the parameters. It is an achromatic meta-lens for visible wavelengths. The optical and SEM images are shown here. From the SEM picture, you can see the different integrated resonance unit from edge to edge across the 41.86 micron diameter. The achromatic focusing spots of the wavelengths from 420 nanometer to 650 nanometer can be observed from the experimental and theoretic results. Achromatic meta-lens for transmission. This is our gallium nitride broadband achromatic optic meta-lens in transmission mode. With the similar design principle I shared with you previously, we design and fabricate transmission type achromatic meta-lens using gallium nitride. Shown here are the SEM pictures of the narrow antennas. The diameter of the lens is 50 micron. The focal length is 235 micron, and the numerical aperture is 0.106. The working wavelength is from 400 nanometer to 670 nanometer. There are more than 52,000 narrow antenna units in this meta-lens. Following the same design principle I previously mentioned, this is the lookup table of all the building blocks and parameters. The unit antenna consists of 800 nanometer height narrow rod or 800 nanometer depth narrow cavities with their dimensions shown here. Both 800 nanometer height narrow rods and the 800 nanometer depth narrow cavities can work as narrow antenna to cover the optic phase change of 2 pi and with high efficiency. The reason for choosing gallium nitride for its high power handling capability, excellent efficiency, and strong and stable physical properties. The standard semiconductor microelectronics process can be used for the fabrication of gallium nitride narrow antenna array and the meta-lens. As shown in the SEM pictures here, high aspect ratio gallium nitride narrow antenna array and the meta-lens can be made. This is the experimental setup for measuring the focal length of our meta-lens. The experimental measurements of the focal length clearly shown the achromatic focusing from 400 nanometer to 660 nanometer across the full band of the visible wavelengths. For comparison, we made 3 achromatic meta-lenses with different numerical aperture values and the efficiencies. The full width half maxima of their focusing spot are also shown here, which are close to the diffraction limit values. The efficiency is defined as the ratio of the optic power of the focused circularly polarized beam to the optic power of the incident beam with opposite helicity. The highest efficiency can be up to 67%, while the average efficiency is about 40% over the whole working bandwidth. The resolution test chart, illuminated by an incoherent white light source. Our meta-lens can resolve the last element in the group 7, which the line width is around 2.2 micron. Most important thing here is that we are able to image full color images by using our broadband achromatic meta-lens. As far as we know that our broadband achromatic meta-lens demonstrate the first meta-lens full color imaging. These are colorful images obtained by our 50 micron diameter broadband achromatic meta-lens. Our broadband achromatic meta-lens demonstrate the first meta-lens full color image movie as well. These are full color movies taken by our 50 micron diameter broadband achromatic meta-lens. Live field imaging and sensing. Many people would like to make large diameter meta-lens to replace the traditional optic glass lenses. However, we consider the advantages of the small diameter of the meta-lens. The reason is clear, as shown here. For small aperture, the depth of the field is large. For imaging purpose, the advantages of the large depth of the field can be found from nature creator. The eyes of the ants and the fruit flies are around the similar size as our meta-lens. They all have large depths of field for imaging purpose. There are around 80 lenses each side for the eyes of the ant and 800 lenses each side for the eyes of Drosophila, so-called fruit flies. Coensia is so-called killer flies. There are around 2,300 lenses each side for the eyes of coherencia. Coherencia is 3 times faster and sensitive than fruit flies because they got more lenses of their eyes. We learn from the nature creator that insects have small lenses and compound eyes. The advantages are large depths of the field and high sensitivity in optic imaging. For this reason, we design and fabricate 60 by 60 broadband achromatic metal lens array. The diameter is 20 micron and the focal length is 42 micron. As shown in the optic photo, we made 3600 gallium nitride achromatic metal lenses in 1.2 mm by 1.2 mm area. The SEM picture displays the 20 micron diameter metal lens array, which follows the same design principle and the fabrication procedure I previously mentioned. These are the SEM pictures of the 3600 gallium nitride achromatic metal lens array. The SEM images clearly show the narrow antenna of each metal lens. These are 9350 gallium nitride narrow antennas for each gallium nitride achromatic metal lens as shown in the SEM pictures. Altogether, there are 33 million gallium nitride narrow antennas in this achromatic metal lens array. Using compound lens for live field imaging was not so much successful due to many problems of the lenses array, spheric aberration, chromatic aberration, and so on. However, for our achromatic metal lens array, it is flat optics without spheric aberration and no chromatic aberration either, and there is no defects problem of the molding glass lens array. This is the experimental setup for live field imaging using our achromatic metal lens array. 3 objects located at different positions can be simultaneously imaging through our achromatic metal lens array. A family camera is used to take the image as shown in this slide. It is so-called live field images. Very simple algorithm is used to compare the images of the objects with the adjacent one, and the depth or distance of the object can be easily found. It is so-called live field imaging method. The disparity of 4 nearest images can provide the precise depth information of the object. The depth information can be used to form the depth mapping image as shown here. In our experiments, we move a space rocket from Earth to other planet. The depth image can display the changes with the time, we show that the velocity of the space rocket can be measured in this way. This is a movie of this experiment. In addition, with our 60 by 60 meta-lens array, we found that under the incoherent white light illumination, the first set pattern of group 8 on the standard test chart can be resolved. That is around 1.95 micron line resolution. Prospects and the summary. We found that our 60 by 60 gallium nitride broadband achromatic meta-lens array with 33 million narrow antennas is small and accurate, high efficiency, with large depths of field, rigid and strong, low profile configuration, low energy consumption, and CMOS process compatible. With the strong demanding of the multi-lens optics system, the advantages of our meta-lens array are very obvious. However, we do not aim to replace the traditional optic lenses. We want our meta-lens to have novel functions which is not available by the traditional optic lenses. For new applications on machine vision, AR, VR, autonomous robot sensing, future drone, mini imaging for medical, so on. Meta-lens is considered as the top 10 emerging technologies in the World Economic Forum 2019. In fact, that we found there are many possibilities for meta-lens to be used for the top 10 emerging technologies for 2020. For example, for quantum computing, the basic problem which hinders the high-dimensional optic quantum entanglement is the decay and the loss of originality in the cascading process of quantum entangled light source. For optic quantum entangled chip, we design and fabricate the meta-surface lens array with the meta-lens size much smaller than the incident light beam and integrate it with a very thin beryllium borate (BBO) nonlinear crystal to form an optic chip. The entangled photon pairs can be generated by each of the focused spots in this optic chip without all the problems of cascaded light source. This is an optic picture of a 10 by 10 meta-surface lens array, and the diameter of each meta-lens is 100 micron. The scanning electron microscope image shows narrow antennas. The entangled photon pairs can be seen in the picture. Our results show 100 entangled photon pairs can be generated simultaneously. All the photon pairs are correlated and the polarization entangled. Shown here in the dashed boxes, 2 photon pairs, 3 photon pairs, and 4 photon pairs quantum entangled states were measured and characterized. The reconstructed density matrices of their quantum state tomography measurements are shown. The results displayed very high fidelities to the pure quantum states. The fidelities for the 2-dimension, 3-dimension, and the 4-dimension entangled states are 98.4%, 96.6%, and 95%, respectively. In digital computing science, 0 and 1 are used to be the binary variables. In quantum science, the states of a quantum bit could be the superposition by the 2 basic states, for example, H and V. The number of states of a qubit is more than the classical bit. Qubit is a d-dimensional extension of a quantum system. As shown in the picture, for our high-dimensional quantum entangled optic chip, the mutual entanglement of 100 photon pairs provides even more possible states and degrees of freedom. This important breakthrough will help quantum information science and technology to realize many applications in our daily life in the near future, such as internet security, e-banking, online transactions, mobile communications, so on, and the other applications on machine learning, artificial intelligence, and the neural network. To summarize my talk, I first introduce the meta-surface, meta-devices, general design principle, meta-lens, differential phase equation, edge alignment method, integrated resonance unit to you. Examples of the reflection and transmission achromatic meta-lenses were shown to you for broadband full-color imaging. I also demonstrate multi-dimensional optic sensing and imaging using our achromatic meta-lens array. Meta-lens array for high-dimensional quantum entanglement light source optic chip is displayed as well. I trust that small and flat is the beauty and great advantage. Most importantly, the future is on the novel function which is not available by the traditional optical lenses. Many thanks for your attentions. You are very welcome for the research collaboration and visiting us. I sincerely hope that I can present my talk in person in Ottawa in the near future. Thank you.
So that was an amazing talk. I'm very excited. I will have to go back and look at it a number of times because there were so many things inside the talk.